about the case a fin with insulated end, and we have concluded here the temperature distribution in case of fin with an insulated end is derived as theta by theta 0 is equal to cos h m of L minus x divided by m minus x divided by cos HML cos HML we have derived equation, and now and also we have derived an equation for theta q0 is equal to heat transfer q0 at the base is defined as square root of hpka theta 0 into tan HML. We have derived the equation now. And also we have given a graph which talks about it, the relation between heat transfer and again that what is called as a ml. When ml is increasing from 0 to 0.3 mm, the heat transfer q is keeps on increasing, this q0 keeps on increasing up to 0.3, and again it assumes a asymptote. After that it won't be any change in that heat transfer is concerned. Similarly, and I have talked about other case also, this one theta by theta 0 1 HML also I have shown here the diagram related to that. Okay, so this that's where we have stopped in the previous class. Today we'll be going to discuss about some more topics like case 4, case 3 and case 4, and again generalized fin equation, generally which is used for any fin configuration, that we will be going to discuss about it. And again the next topic we will be discussing about is efficiency and effectiveness of fins, and with some problems we will try to do with today's class. Okay, as the time permits we will try to do some of the problems in this class itself. Okay, let me go through that. The next case, which is called as a case, the case 3, the what case 3 talks about is uh, it is the case 3. I'll write that case 3. What is the case 3 we are going to discuss? We'll go to that topic case 3 with the new slide. Case 3 is mentioned like this. Case 3 I am mentioning like this. This is case 3 for the fins. If the temperature at the fin tip is TL, then theta suffix L would be small l. I'll write it. Theta L would be TL minus T infinity, TL minus infinity, and the resulting expressions for the temperature distribution and the heat transfer are I'll write the temperature distribution theta by theta 0 is equals to, this you need to mug up, is equals to theta L by theta 0 into sin h mx plus sin h m into L minus x divided by sin h ml. This is the heat transfer. So this is the temperature difference distribution in the case when that tip is maintained at a temperature of TL, and the temperature difference theta L is defined as TL minus T infinity. Right? Means that T infinity is nothing but ambient temperature or surrounding temperature. And Q0 heat transfer rate is defined as, and heat transfer rate at the base is defined as HP Ka to the power of half or square root of HP Ka theta 0 into cos HML minus theta L by theta 0 theta L by theta 0 divided by sin HML. Okay, this will try to derive these equations as the time permits. We will try to derive these equations. Okay, this is equation number 1 and this is equation number 2. That means there are the cases. One we have taken as one of the cases we have insulated tip end, adiabatic end. Another one is nothing but convection off at the end. Means what entire heat transfer is transfer enter through the pin across the length. That one, and again heat transfer we have discussed in the previous classes. Now we have taken the cases like this, and fourth case we will be discussing about it now. The case 4. Case 4. What is that? Case 4 is nothing but for very long fin like L is infinity. Okay, and theta L is going to be 0. Why it is nothing but, see, we had defined that temperature difference theta is equals to T minus T infinity, right? And when it theta is equals to 0 at the base, theta 0 at the base of the fin, theta is equals to when x is equals to 0, this is called as theta 0 and t is equals to t0. Similarly, theta suffix L will be considered when x is equals to L and the temperature is TL minus T infinity. Now in this case, this TL is almost this TL is almost attains T infinity. Therefore, this is equals to theta L is equals to 0, theta tends to 0, right? This is the condition we are going to discuss about it. Now, theta L is tends to 0, means that this is equals to 0 case we are going to consider it now. Okay, for which now this is the case we are going to consider it, for which we already defined what is the theta 0, right? This is theta 0, right? Theta 0 is equals to, I'll write it right. Let me talk about it here, right? The generalized equation, let me talk about it. Generalized heat transfer temperature distribution theta is given as theta is equals to C1 e to the power of mx plus C2 e to the power of minus mx, right? And when x is equals to 0, when x is equals to 0, then theta 0 would become C1 plus C2. Okay, this is generalized equation. Okay, and when theta L is equals to 0, I mean theta L is equals to, if I use theta L is equals to C1 e to the power of m, very long fin, right? Means what? Length is going to x is equals to infinity. Therefore, m to the power of infinity e to the power of m into infinity plus C2 into e to the power of minus m infinity, that is equals to e to the power of infinity. Therefore, C2 is equals to here e to the power of m infinity, this is 0. Therefore, theta L is equals to C2. Okay, this is theta L equal to C2. Alright, now I'll go to that next step. I'll go to next step where now the generalized equation would become theta is equals to, what is the general equation? C1 e to the power of mx plus C2 e to the power of minus mx. Therefore, the generalized equation theta would become, in that case, theta will become C2 is equals to theta L. Therefore, theta L into e to the power of minus mx, and theta L is equals to e to the power of minus mx. Okay, and heat transfer, this is temperature distribution, right? And the heat transfer is given as q is equals to minus ka d theta by dx at x is equals to 0 is given as minus ka d theta by dx can be written as, here I'll write it as d theta by dx is written d by dx of C2 e to the power of minus mx, where C2 is equals to theta 1, okay, theta L, right? So this is equals to minus ka into minus m into C2 into e to the power of minus m, and x is equals to 0, this is equals to 0. Therefore, this is equals to m minus into minus plus ka and theta 0, that is equals to this is equation is where m is equals to square root of hp by ka into ka theta 0, right? So this is the equation, you can remember it for the case when it's very long fin, and that is nothing but x is equals to x tends to infinity and theta L is equals to 0. Then in this case, these are the equations you need to remember it. This one, okay, this one, this is also q at x is equals to 0, okay, q0 or q naught is equals to 0. So these are some of the equations you need to remember it, okay. Or I will try to give the summary of all the equations what we have derived by case I will try to give today, and then I will go to the next topic. Alright, so now I will be making a chart which talks about all the cases what we have derived so far in the case of a fin. I will write first, I will take lines. First one, serial number, okay, sorry, I'll start from here. This is serial number. Okay, tip condition, fin tip condition. This is tip condition. Okay, I will write here. I'll draw a column and tip condition, and then temperature distribution for expression. Temperature distribution, then fin heat transfer rate. Fin heat transfer rate. Okay. Now, first case, first case, convective tip. Convective tip case, that is nothing but H A theta L, right? H theta at L is equals to minus K d theta by dx, which we have already read at x is equals to L, is given as the equation we have derived temperature distribution is theta by theta 0 is equals to cos h m into L minus x plus h by mk into sin h m of L minus x divided by sin h m of L minus x plus h by mk sin hml. This we have derived already, this equation we have derived. And the heat transfer is derived as, see, here I can use m, heat transfer rate, fin heat transfer rate I can use as m into that what I have derived, I will try to draw it other way, m into m into tan hml plus h by mk divided by 1 plus h by mk tan hml. We have derived this equation in the first case, of it. Okay, and then I'll go to the second case, adiabatic tip. What we have derived? Adiabatic tip, diabatic fin tip, that is d theta by dx at x is equals to L is equals to 0. At x is equals to 0 is 0. In that case, the temperature distribution what we are defined in nothing but cos h m of L minus x divided by cos h ml, and here the heat transfer rate is defined as m into tan h ml. Okay, this we have derived. Okay, now similarly the third case, just now today we have defined fixed tip. Fixed tip means what? Some temperature is given at the tip, that is x is equals to that is T is equals to T1 or TL is given at the fin tip, that is theta L is given as theta L, and the equation we have shown today, theta L by theta 0 sin HMX plus sin HM of L minus X divided by sin HML, and here the heat transfer coefficient, what we had heat transfer rate what we had derived is, you can see here, heat transfer rate is given as this one, cos HML minus M into cos HML minus theta L by theta 0 divided by sin HML, right? Here cos sin HML. Okay, this is third case. Now I will be going for fourth case. Fourth case as infinite fin tip, is means it is not a finite tip, infinite tip where x, we used to say x is equal to L. Now here this L is length is infinity and theta L is equals to 0. In that case, this is equals to temperature distribution theta by theta L is equals to e to the power of minus mx. You can check here, theta by theta x is equal theta L is equals to e to the power of minus x, and heat transfer is square root of hpka theta 0. Now this is equals to, what we derived is nothing but, which is q is equals to mk mka theta 0, right? Mka theta 0, this we have derived it, okay, where m is equal to, you can, okay, where m is equal to square root of hpka. Okay, these are the derivations what we have discussed so far in the classes. Now we'll, as I pointed out, we'll be going to discuss about generalized equation for fins, like what we have derived for temperature distribution for a Cartesian coordinates, like that, what, how we are going to define generalized equation for fins. Okay, now the next heading is going to be generalized equation for fins. Okay, for this I will take again the fins shape like this. uh, I have taken a fin of such a shape, and I have a section here. Okay, and if I see that small element in 3D, it is like this. This I have taken as a small element, and this is end of the fin. Okay, this fin is attached to the base. Okay, attached to the base. The base is like this, looks like a circular, like this. Okay, Now from this, at a distance of x, at a distance of x, I have considered an element of thickness dx, and which has got a perimeter which is varies with respect to x, p of x, and area of cross section also varies with length x, and here it is convected heat like this, q convection. Okay, and to this heat is conducted like this, qx. Okay, and after it crossing this element, I will take this is q x plus dx. Okay, like this. Okay, and the fin base temperature is T0, and the outside temperature of the fluid has got a convective heat transfer coefficient H, and the temperature, surrounding temperature is T infinity. Okay, so for this configuration, I need to derive generalized heat transfer equation. Okay, now we will try to write once this setup is made, and now I will write the energy balance for this energy balance. I am writing it. The energy balance for this energy interactions is Qx is coming in to the small elemental strip, and this small element can able to convect the heat, right? Q convection out, and this can able to dissipate heat in the form of Qx plus dx. Okay, now if Qx is by conduction, then I can write the Fourier equation Ka into d temperature along x direction divided by dx is equals to convection. I will write it as h into perimeter px. This is already mentioned, perimeter px into dx into what is the temperature difference is nothing but I am considering here the temperature at this point is T, therefore Tx minus T infinity, right, plus Qx plus dx is nothing but minus Ka. This already we are aware of it, how to write Qx plus dx, minus Ka dt by dx plus d by dx of minus Ka dt of x divided by dt into dx, and this square bracket close, right? Now this minus Ka dt by dx, this when it goes this will go into get cancelled, right? Now the remaining will be, and this dx and this dx is also gets cancelled. When it's both gets cancelled, then therefore the equation is going to be d by dx of Ka dtx by dx is equals to h p minus, if it minus is there, it comes to left hand side it's going to be positive, therefore d by dx is equal to hp t infinity tx minus t infinity tx minus t infinity. Now here, since if you see here a is there and p is there, I am trying to find out one dimensional generalized heat transfer equation. Then if a and p are and a and p are, this is area of cross section, are a function of temp. As the x is increases, this is going to vary the a and p. Therefore a and p are functions of x x. Therefore the above equation, therefore this is the equation, can be written as k a is a function of x into d. If it goes here, d square t of x divided by dx square plus, now I'll be applying product rule here for this equation. d by dx of uv is equals to, how I can use u dv plus v du. The same way I'll use it, ka of x d square t by dx square and dA of x by dx and k dtx of dx is equals to hp of t of x minus t infinity. Okay, right? I write it. This is, I'm writing as, this is u and this is v. Therefore, I wrote like this. Okay. Now, this is equation number one. If I use this is equation number one, if I name this as equation number one, now this equation is, I am dividing throughout. This equation number one is dividing throughout by Ka, and I'm simplifying this tx minus t infinity as theta x and putting t of x minus t infinity as theta of x. Then this equation will become, this equation dividing throughout by Ka, therefore the equation will become d square theta of x. T, as I said already, t is a function of this one, therefore d square theta of x divided by dx square plus d, this is d theta by dx, d theta by dx, d theta of x divided by dx into, if I divide by Ka, what will happen? K will get result, therefore dA of x divided by dA, and if I bring this hp of tx minus t infinity is nothing but theta x. If I bring it towards leftward side, this is equals to minus hp and divided by Ka, therefore this is Ka into theta of x is equals to 0. This is the generalized equation. We will need to remember it for a fin. Okay, so the fin generalized equation is nothing but d square theta of x divided by dx square plus d theta of x divided by dx into dA by dx minus hp by Ka is equals to theta x. And this hp you can write it as hp by Ka. Already we have used the equation hp by Ka is equals to m square. You can use it, that m square here, okay, in the equation. So this equation we call it generalized equation for fins. Like what is we have derived for a temperature distribution, generalized equation for heat transfer equation for a one dimensional heat transfer. Right now, with this background and this with this background of various fin configurations and its temperature distribution in case of a fins, rectangular fins. Now I will be going to define one more important formulae or other important relations like efficiency and effectiveness of fins. Okay, that I will be covering now. Next topic is as next topic. Now I will be going to derive expressions for efficiency and effectiveness of fins. Efficiency and effective effectiveness of fins. So first I will be defining efficiency. Efficiency. Efficiency is defined as the ratio of defined as the ratio of actual heat transfer by a fin, heat transferred by a fin to the maximum heat transferred to the maximum heat transferred by fin if the entire fin area were or at base temperature, at base temperature, right? So means efficiency is defined as actual heat transferred by a fin. I'll write it as the actual heat transferred by a fin. I'll write it as this efficiency of fin I am denoting as eta fin is equals to actual heat transferred by fin. I'll write it as q fin divided by maximum heat transferred by a fin when the entire fin area were assumed to have the same base temperature base temperature, that is the efficiency of fin is equal to q fin by q max. Okay, right, this is the formula you need to remember it. Efficiency of fin is equal to q fin divided by q max. Now we will go some cases like that. For infinite rectangular fin, for an infinite rectangular fin, eta fin is equals to hpka into theta 0 divided by hpl into theta 0. This theta 0 gets cancelled, and this is equals to, I can write it as hpl whole square root hpl whole square. Therefore square root of ka by hp into 1 by L square, that is equals to 1 by this is Ka by this is Ka by HPL square. This is equal to, this I can write as 1 by M L. Okay. This is 1 by ml, I can write it. Okay. So this is for infinite area, right? And the next case is for a rectangular fin. Next case I'm taking rectangular fin with an insulated fin tip, with an insulated fin tip. So I'll recall that what we have written in that. Okay. So for insulated fin tip, what is the formula we have used? Okay. So here I have used the formula. This is the formula I have used. Okay. This I am using it here now. Okay. So infinite tip, this is the formula I have used, heat transfer. Now for this I am using this equation. Okay. Now fin tip is equals to fin tip for rectangular fin. This is, instead of, I'll use case one. This is one, and this I am using two. Then in this case, fin efficiency is defined as fin efficiency is equals to square root of HPKA theta 0 tan HML divided by when the entire fin is at the same temperature. Therefore, the equation is HPL theta 0. Right now, therefore, the equation is becomes now efficiency of fin is equals to tan theta 0 gets tan H ml divided by ml, where m is equal to square root of hp by ka, right? Okay, so this is the case which relates to rectangular fin of insulation tip with insulation tip, right? So these two equations, you just remember it. Now sometimes there is a situation like if the fin is sufficiently wide, then the turn 2W will be large compared with 2T, right? Now, now if the fin is sufficiently wide, is sufficiently wide, then the term perimeter in the perimeter, then the term 2W will be large compared with 2T, 2T, then ml is written as square root of, what is that, ml hp by k, right? Therefore ml is written as 2hw divided by ka, kt into w into l. Therefore w gets cancelled and 2h by kt will remain, into l will remain. This is written as square root of 2h by kt into l. This can also be written as square root of 2h by kt into l to the power of 3 by 2. I can write it as, okay, means what, ultimately it goes into get l, uh, that is equals to, I can write it as square root of 2h by KAM into L to the power of 3 by 2. Okay, where 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 T into L written as AM is nothing but profile area of fin. Profile area is the profile area of the fin. Therefore, ML would become square root of 2h by KAM, where AM is profile area of fin into L to the power of 3 by 2. Okay, L to the power of 3 by 2. Now, I'll go to the real fins shapes. For a real rectangular fin, for a real rectangular fin, which is long, wide, and thin. So I am going for a real rectangular fin which is of long, wide, and thin. The efficiency can be calculated by equation. What is that? Eta fin is equals to tan h ml by ml is by ml. Indeed, L is going to be replaced with the corrected length. Okay, it is given by Gardner and Kodanraman in 1997. So this L is going to be replaced with LC. This how do you calculate this LC? We'll talk about now. Okay, this is given by Gardner and Kodanraman. Okay, that's we'll talk about it now. Means this LC is going to be, we'll try to write it as LC is equals to L plus T by 2. Okay, this is equation 3, right? So means instead of L will be since it is a wide and long, so the corrected length we are taking as L plus T by 2. This corrected length is going to be compensates the fact that there is a convective heat loss from the tip of a real fin. Okay, this corrected length is going to be taken the fact that there is a convective heat loss from the real fin tip. This taken care of it. Okay, so this that LC is equals to L plus T by 2. Okay. Now, so then when you consider this also in the equation, now efficiency of fin would become tan H of M is equals to M is equals to, how do you calculate what is that equation? HA by KA. Therefore this is equals to ML, already I have written as ML is equals to square root of 2h by KM. So I will try to write it. Tan H of square root of 2h by KT of, just a second, 2h by KT of L plus T by 2. L plus T by 2 divided by M is square root of 2h by kt of L plus T by 2. Okay, this is the equation, you can remember it. Okay, see, you can check here. Ml is equals to, yeah, you have mentioned Ml is equals to square root of 2h by kt into L. The same only I have used here. Ml is equals to tan h, M is equals to 2h by kt into L, where L is going to be replaced with LC, corrected length, that is equals to L plus T by 2 divided by square root of 2h by kt into L plus T by 2. And the heat flow becomes, Q is equals to square root of HPKA into theta 0 tan h of square root of 2h by kt into L plus T by 2 this is equals to efficiency of fin. Just now I have defined it as nothing but Q fin by Q max, right? Therefore then what I can do, Q fin is equals to efficiency into fin efficiency into, I'll write it here, fin efficiency into actual maximum possible heat transfer, therefore HP into HP into corrected length LC into theta 0. Okay, this you can use it. Okay, right. So now these are the some of the procedures I have talked about. Now we want to calculate LC and AAM for straight rectangular fin. Now I'll try to talk about some more information now here. Now I'll insert some of the graphs, some of the pictures here. Such pictures. I will take picture here. Okay. Now, so here a diagram figure shows efficiency of a rectangular fin and triangular fin. And again, the diagram which shows the efficiency of circumferential fins of rectangular profiles. There are two diagrams I have shown here. One is rectangular profile and again triangular profile fin, and another one circumferential with the rectangular profiles. Okay, so to find out this actual heat transfer or the efficiency, how do you calculate that efficiency values for rectangular configuration, which is shown here, and which is shown as a triangular configuration? How do you calculate? Okay, to calculate, I will try to talk about step by step procedure how to do it. First case is, first one, calculate LC and AM. Calculate LC and AM. To calculate LC and AM. Now, in case of a rectangular fin, which is a straight and rectangular fin, he has given that LC is equals to L plus T by 2, and AM is also given as T into LC. AM is also given as T into LC, where is profile area of the fin. Okay, so once you know for rectangular fin, LC is equals to L plus T by 2 and AM is equals to T into LC, T into LC. And in case of a triangular fin, this is rectangular fin. Calculate LC and LM. LC is given, LC and AM is given in the figure. Then in case of a triangular fin, half into AB, area is going to be therefore for a triangular fin, LC is given as L only, okay, and profile area, fin profile area, mean fin profile area AM is equals to half into T into LC, okay, this, okay, once you know it, right, these are the two shapes, the fin shapes you got it, okay. Now I am going to the third case in case of a circumferential fin, which is shown here for the circumferential circumferential fin, okay, which is of rectangular cross section. That shape is also shown here. This is circumferential. It is something like this, and this is the thickness, and again this is the thickness. You can see it here. Okay, so this R1 maybe, and this is going to be R2. This is going to be R2. It is shown here, and this is the length of the fin L. It is shown here. Okay. Now in this case, when you want to find out the L, this L, when you want to find out the L is equals to, is given as L is equals to R2 minus R1, and but I want corrected length, therefore LC is equals to L plus T by 2, and corrected outside area, radius of the fin is given as R1. See, this is R1. Instead of R2, what you are doing is R1 plus L2C you are using it. R1 plus LC, okay, where LC is equal to L plus T by 2, okay, and AM you will be using profile area, fin profile area is equals to the same formula, R2C minus R1 into T, right? You can check it here. It is already in the figure. It is shown like this. AM is equals to T into R2C minus R1. Okay. Now, once you know this one, for the case of circumferential fin of cross rectangle cross section area, you need to find out R2C by R1. Then you will get some value. With the help of this value, with the help of this value, you can able to find out the efficiency. When R2C by R is equals to 4, you have to follow this graph. When R2C by R is equals to 3, you have to follow this graph. When R2C by R is equals to 2, you can follow this graph. Okay, so this is something you need to remember it. Okay, so if in the problems given like this, a fin of a rectangular fin of uniform cross section, you can go for a triangular fin. It is given as such case, you can go for it. And again, circumferential fin of rectangular cross section, you can follow this section 2, this is figure 2, and then the LC and R2C and AM, how to calculate it also I have mentioned here. Okay, once you know this LC and again AM, then you can able to find out Q max, right? Now Q max, calculate Q max. So for it, when you want to calculate Q max, why these are all you are doing, it is nothing. Efficiency of a fin is equals to actual heat transferred by fin divided by maximum possible heat transferred by fin. Therefore Q max, when you want to calculate Q max, then first, for rectangular or triangular fin of unit depth, Q max is equals to HPLC into theta 0, right? Q max is equals to, you can check this diagram here. right? Qmax is equals to, I am assuming this entire fin is of a base temperature, therefore I can use that HP into HA, that is equals to HA, area of profile is equals to, here it is mentioned, therefore HP into, you can check it, HP into LC into theta 0, right? This is for fin of rectangular or triangular fins, and for circumferential fin this is for rectangular or triangular fin. For circumferential fin, Q max is equals to HA is equals to 2 pi of R2 C square minus R1 square into theta 0. This is for circumferential fin. Okay. So means you have calculated Q max. Now once you calculate Q max, now I'll be finding out Q fin is equals to efficiency of a fin minus into Q max, right? So this is going to be get that Q fin, right? And sometimes you are asked to calculate total heat transferred from a fin surface. If you are asked to calculate total heat transferred from fin surface is equal to Q total is equal to Q primary surface, heat transferred from primary surface, plus Q fin, that is equals to total heat transferred from a fin surface